This recording is a continuation of a recording that was talking about blood flow when we were talking about different concepts associated with circulation or hemodynamics. So as a reminder, flow is equal to pressure difference, the delta P, over R, which is resistance. So increased resistance would decrease flow. A decrease in resistance would increase flow. So the next concepts I'm going to look at somehow relate to this. So first one is the role of turbulence. If you have turbulent flow, and turbulent flow can be caused by anything that interferes with smooth blood flow. An increase in turbulence can increase resistance, which would slow blood flow. So what can create turbulence? So if you have a very high flow rate, that can create turbulence. If you have a sudden change in the vessel diameter, so if you go from, say, here and then like, oops, narrow, that can create turbulent blood flow. If the blood flow is flowing around in a regular surface, so if I have, say, atherosclerotic plaques, that can create resistance. Now, what is this turbulence? Well, normal smooth flow is laminar. So the idea is you have a blood vessel, they flow like sheets, layers. But because, I'm just going to let you know, because of the friction that you get along the wall, the blood flow actually is slower here close to the wall than it is here, so it actually forms kind of, we call it parabolic surface. So, but here's are your layers, so it's like this. Now, what would happen if it, say, encounters a sudden change in vessel diameter or a regular surface? What happens is these layers start to mix with each other and it creates turbulence. And one of the things I want you to think about it, because I think you probably know exactly what I'm trying to mention, is what is the effect of velocity, flow rate on turbulence. Is, if you think about it, if you've ever been in a vehicle that, it's not a sports car, and you speed and you get up to a certain critical velocity where that car starts to shake. And I've been in one of those where the car was not designed to go very fast. Once you got to a certain velocity, it started to shake. Turbulence was created. That's kind of what I'm trying to explain to you. So certain velocity, certain speed of flow, depending on the vessel, that can create turbulence. Just think about turbulence as like when you're flying in a plane, is you've got some of the, you've got a storm coming in, you've got some of the air is mixing in there, and then the plane hits it, that creates turbulence. And turbulence can increase resistance, going to make it harder for that plane to get through that. So that's why we're going to change the altitude, we're going to get up above this system or whatever, is I want to, if that turbulence increases resistance, that's going to slow blood flow. Turbulence is actually relatively uncommon in smaller vessels unless there's some sort of plaquing, atherosclerotic plaques, or if they're scarred. And actually a term, I'll actually apply this to something you've heard of before, is turbulence does create vibrations, and you can hear them. So think about when you're listening for heart sounds. It's because you're listening to the turbulence created by that blood being redirected in the heart. It creates vibrations that you hear. The same can apply to your blood vessels. If you have turbulent flow, it can create some vibrations that we can hear, but they're actually referred to as bruits. This is how you pronounce it. This is how you spell it, bruits. You can detect a bruit if you place a stethoscope over a subject's thyroid gland if they have hyperthyroidism, because they have higher flow rate there in that thyroid gland, and so a bruit could be detected. If if you place the stethoscope on someone's over the carotid, you may hear a bruit if they've got some plaquing. That's not a good sign if they have it, because you shouldn't hear any sounds associated with those. If you place on a normal blood vessel, you shouldn't hear any sounds. So what would happen is, if you have turbulent flow, that increased resistance, which can slow blood flow. Your heart's like, no, 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 I want to make sure that flow gets to where I need to get a certain amount of blood to all these tissues. The heart's going to have to work harder. So there's the downward thing, is the heart's going to have to work harder if it encounters resistance. Another thing I want to look at is the relationship between velocity and this, that's flow, and the A is total cross-sectional area. So what's the relationship between total cross-sectional area and the velocity of blood flow? Now, I'm not going to really look at the flow because we try to keep flow rate relatively constant. So this is what I want to address, is the relationship between total cross-sectional area and the velocity of blood flow. So I have to make the distinction of what the Q, though, is versus V. So Q is a flow rate. It's a volume per unit time. Velocity is a distance traveled per unit time. They're different. So velocity, think of as speed. So here we have two parts of this tube. This one, the area is 1 square centimeter. This one is 12 square centimeters. And what it's saying is here, the flow rate is the same through both of those. It's 12 cubic centimeters per meter, or 12 mils, or sorry, per minute, 12 mils per minute. How could that happen? How could you have the same flow rate despite differences in cross-sectional area? The reason is that even though this is smaller, it has a higher velocity. We're getting more through that per unit time. And that's an important concept, is the greater the total cross-sectional area, because it's on the denominator, so I'm going to write it this way so you can see it. That's on the denominator. The greater the total cross-sectional area, the lower the velocity of blood flow. The lower the cross-sectional area, the higher the velocity of blood flow. What is that significance in our circulation? Well, our circulation, think of as this, is say being your aorta. You've got one, that's it. These represent your capillaries. You have a lot more capillaries than you do an aorta. So we're looking at the relationship of total cross-sectional area and velocity of blood flow. We have here, this represents the capillaries right there. That represents the capillaries. You notice the highest total cross-sectional areas in the capillaries in our circulation, and it has the lowest velocity of blood flow. What's significant about that? What's happening in the capillaries? Capillaries is where we're going to have exchange. So I'm getting I'm getting that blood to the capillaries, and the capillaries are delivering blood to tissues. I'm going to have exchange. I want to give some time to have the exchange that takes place. So the velocity of blood flow is the lowest in our capillaries than it is anywhere else. Think about like going from the aorta to the arteries all the way down. It's just trying to get blood to those capillaries. So you just want to get there fast. The capillaries have the largest total cross-sectional area. This has the lowest velocity of blood flow. I want you to think about it another way. If you've ever been out in nature, you got a river, and so you see a leaf, and it's flowing down the river, okay? That river kind of narrows. Watch what that leaf does. It travels a lot faster through that river. So that's showing you that same concept. As the cross-sectional area decreases, the velocity of blood flow increases. So I want you to keep that in mind. So it's another important concept associated with the circulation. So we looked at blood flow, factors that affect blood flow, the role of resistance in blood flow, its role in resistance, and the last one is the relationship between total cross-sectional area and velocity of blood flow. Other concepts that we will be looking at is we're going to be looking at your arterial blood pressure. And at some point we'll be even talking about the regulation of it, but we'll do that a little bit later. But we'll also be looking at capillary exchange. And later also we'll be looking at things such as the regulation of blood flow and blood pressure. So we'll end up here.